basically, okay, just excuse me, just I don't know why it is not working. Okay, now it is okay. The next slide.
Yes.
Is it visible now?
Yes.
Okay. So these are the outlines of my talk today. Now, as usual, first chapter goes to the introduction, basically introduction about the quasi-isometry and quasi-isometric group of the real line or the Euclidean spaces, and then goes to the main concluding chapter, the structure theorem of the group QIR. Then go to the some properties of that group QIR. That means the left variability or local indecibility of the group QIR, and then we go to the we extend the idea from QIR to QIRN to find some properties and some criteria for the elements which are belong to that set or that group QIRN. And chapter 5 basically goes to the structural and some properties of the group PL delta. And the last chapter goes to, as usual, conclusions and future scopes. And then we go to reference. So first we go to the chapter 1, introduction. So this basically we all know that the quasi-isometry basically one of the central or the fundamental concept in geometric group theory, and we all know the definition. But still, I am just elaborating the definition properly. That if there is a map from a metric space X to X prime, then we say that that map is said to be quasi-isometric embedding if this inequality holds, that 1 by m and this holds basically for some m greater than 1 for all x1 x2 belongs to the domain set. And in addition, if there exists an m prime such that for any y belongs to the codomain set such that the distance between fx and y is less than m prime, then we can say that this f is a quasi-isometry. And interestingly, if there are two maps, if f and g and two maps from a same space, suppose we are taking some same space to same space, that means x to x, they are said to be quasi-isometrically equivalent if there exists a constant alpha such that the distance between fx and gx should be less than alpha. And this relation basically is an equivalence relation, we can check easily. This relation basically this equivalence relation forms a basically this, let class f denote the equivalence class of a quasi-isometry f from x to x. And we denote the all classes of quasi-isometries from x to x by qix. And this set basically forms a group. So that is our main idea, that the group forms in this way actually. So this set forms a group with our usual mapping composition. And there are some interesting facts are there that if we can check it also easily, that if there's a quasi-isometry from x to x prime, then always for the space x we can form a group qix, and for x prime also we can form a group qix prime. So if there is a quasi-isometry from the space x to x prime, then the corresponding group for x, that is qix, and for x prime qix prime, they're isomorphic. And for example, suppose if there are from R to Z, the T goes to box T is a quasi-isometry. So we can say that the group QIR and QIZ are isomorphic as a group. So now we go to some notations that is actually used in my talk. So PLR basically denote the set of all piecewise linear homeomorphisms F from the real line to real line. PL delta R means the set of all functions which are in PLR such that the slope of that functions are bounded, basically lambda f is the slope of f. So that slope of that function are bounded by, that is PL delta R. And PLKR means basically the set of all piecewise linear homeomorphisms of R with compact support. Diffeomorphism of S1 means the all set of all C infinity diffeomorphisms, the circle H1. QIR in general quasi-isometry of the real line. QI plus R means basically the orientation preserving quasi-isometric group of the real line. And similarly, QIR plus or QIR minus denote the quasi-isometric group of the positive real line or negative real line, including 0. So basically now we go to some literature survey. From this literature survey, we basically got the direction of my research mainly. Actually, my main aim is this talk. Actually, my main aim is that to characterize the group QIR more explicitly, and we can characterize some properties of the group QIR. That is my main aim, to characterize the group QIR, or you can say QIRN also. So these are the first information about the group QIR. That means in the sense of characterization, that That is a natural homomorphism phi from PL delta R to QIR. That is surjective basically. So it is proved by Sankaran in 2005, and he also proved that some well-known groups like the lifting group of diffeomorphism S1, lifting group of PLS1, the group PLKR, as well as the Thomson group F, and the free group of rank C. These type of groups are embedded in the group QIR, making that the group QIR is more interesting to study basically. And by using this result, in 2016, Chakraborty proved that the center of the group QIR is trivial. That is also interesting result. So then in 2019, Mitra and Sankaran proved some extension of the previous result. That means the following groups are embedded in the group QIZN, like bilipsy of Sn-1, diffeomorphism of Sn-1, PL-Sn-1, this type of groups. And in recently 2023, Ye and Zhao proved an interesting result that the group quasi-isometric group, I mean the orientation preserving quasi-isometric group, the real line is left quadrupole but not simple. And they also proved that this group cannot act on the real line. This also, I mean, they prove also this result. So these three results is very much interesting. That means that orientation preserving quasi-isometric group of the real line is left quadrupole but not simple, and this group cannot act on the real line. So by using this type of results or literature survey, we study our result on that group QIR, or specifically QI plus R, you can say. So now we go to some properties that properties of that group. Which groups
you go back to the previous page?
Yes.
So here, this you don't really mean bilipids from Dn to Sn-1, right? Because they are not bilipids. Is it just lipids?
Which one? Bilipids of Dn, Sn-1.
Yeah. So there's the first theorem. There's the second part. There's bilipids Dn Sn-1. Do you just mean Lipschitz maps? They are not bilipids.
Basically, we are taking that maps from Dn to Dn, and which are basically the boundary of that map at Sn-1. We are taking the collection of bilipids map. I think I don't know. I think it is in the literature survey they proved that in this type of result, the bilipids of Dn, Sn-1, that group specifically embeds in QIZN. I can see you that the result actually in that paper in the further. Okay. You are saying that this is not a bilipids map. I mean, there is no bilipids from that type of case.
Okay.
Yes. Can I go?
Proceed? Yes.
Okay. So we go to some properties of that group. That groups are embedded in the group QIR, or you can say QI plus R. So that group PLKR is simple. The lifting of that diffeomorphism S1 contains a free group of the rank of the continuum. The commutator subgroup is a simple group. If the proper quotient group of that F is abelian and F doesn't contain an all-abelian free subgroup. Basically, I am just discussing these properties because these groups are embedded in the group QIR. That making that the group QIR is more interesting to study. That's why I'm just discussing this type of properties. So now we go to our main contributing chapter, the structure theorem of QIR. Basically, since this group is a infinitesimal group, not the finite group, so basically this type of groups to compute or to explicit description of all the elements of QIR is very difficult to compute. So that's why we are just compute only some portion of that group. Or we are taking a quotient of that group and explicitly describe the elements of the group, that quotient group. That is the main idea. So in 2023, Ye and Zhao proved that a group QIR is isomorphic to that QI plus R semi-rate product T, where T is the reflection as usual, Tx equal to minus x. So then he proved that, interestingly, that this group H equal to all those elements class A belongs to QIR plus. QIR plus means the set of all the quasi-isometric group of the positive real line. So such that limit of fx by x is 1. This set is a normal subgroup of the group QIR plus. They proved that actually. So this is an interesting result. So here it is clear that if we can take H prime, looks like that all those elements class A belongs to QIR minus. such that the limit extends to minus infinity fx by x is 1. This also a normal subgroup for qi r minus. And similarly, if we take the direct product h prime, then that is h bar. That is a normal subgroup of the group qi plus r. That is the main observation from this result, normal subgroup of QIR plus. So now we go to explicit description. That means we define and we actually introduce an invariant to study the characterize all the elements or some of the elements of the group QIR plus. So here this is the invariant. That means we introduce this invariant SG by SG equal to the set of all limits of that function gxn by xn such that gxn by xn converges for any class G belongs to QIR plus. So this is the main key of our talk, SG, to compute SG. So we proved that this SG is interestingly a compact and connected subset of R plus. That is very interesting. So since it is compact and connected of R plus, so it is clear that either it is a singleton set or a bounded interval. So for singleton set, we define a set HC that is equal to all those class G belongs to QIR plus such that the limit set is just singleton. And for the interval, we define HI. HI equal to all those class G belongs to QIR plus such that SG equal to I. And we define just HC bar equal to all those HC. I'm taking the union of HC. And note that this obviously HC subset of HI and QIR plus equal to union of HI. So these are the some construction by using SG and then HC, HI and HC bar. So now we go to some results. That means the result is that it can be readily checked that uh, class G belongs to HC. Class G belongs to HC if and only if limit extends to infinity gx by x equal to c. That is also very interesting to our study. That for the first part, it is clear that if limit extends to infinity gx by x is c, then class G belongs to HC. Because HC is nothing but the set of all elements such that the limit is c. So if limit is c, then class G belongs to HC. But conversely, if class G belongs to HC, then if the limit is not equal to c, then we can easily prove that then the contradiction. So ultimately we get class G belongs to HC. So this is a result. So if c equal to 1, basically that is so c equal to 1, then HC is nothing but our H. That H proved by Ye and Zhao in 2023 that this H is a normal subgroup of QIR plus. So if c equal to 1, then we get our own H. So these are some results. Okay, now construction. How can I explicitly describe the elements of the group QIR plus, or you can say QIR plus by a quotient. So here, suppose we can take SG equal to a interval a comma b. We can take because SG is either singleton or interval. So if SG equal to a comma b, then we can choose an element FA inverse belongs to that HC type of element, HA inverse. So such that the S of that of class, that means if A inverse compose G equal to 1 comma A inverse. That means in each element, class G, class H, no matter, always we can get this type of limit set 1 comma something. So that is our main aim, that we can always write for any element G or H, we can write S of FA inverse compose G equal to 1 comma something, or 1 comma M, capital M, we can say. So we can write QIR plus by HC bar quotient, QIR plus quotient HC bar. We can write disjoint union of H1 comma M quotient H. That is the main idea. So basically we want to study only H1 comma M by H, the elements of H1 comma M by H. So if two elements, suppose F comma G belongs to H1 comma M by H, and they are in, their left quotient are same, basically HF equal to HG, then we can write easily by good theoretic property that class F equal to a class of H compose G. Basically now we are constructing how to characterize the elements of QIR plus by HC bar. That is my main aim. That's why we just give some restriction or some we can take some condition. So we are just improving some condition that if class HF equal to HG, then we can write class F equal to class of H compose G, and moreover, if we get a sequence n such that limit gn by n equal to 1, then from above we can say limit fn by n equal to 1. So basically, if no sequence n exists for this case, then they are in different class. Basically, HF and HG are different class. So if we just remember that Paramesh or Shankaran proved that there is a onto homomorphism from the group PL delta R to QIR. But actually, it seems to be challenging to say when two such PL delta, two such piecewise linear homomorphisms lie in the same equivalence class or not. That is a challenging task. That's why we are doing that only. That which elements are in the same class and which elements are not in the same class by using by giving some conditions on slopes of f and g. So now we get that. On the other hand, suppose there exists a strictly increasing sequence n with this condition holds. So these are basically conditions. We are taking conditions, imposing this condition. We want to characterize the elements of that group. So then on the interval n comma n plus 1, we get a partition like this, such that on each of the partition, f and g both are linear, and for each of the intervals we get two R tuples, that means the slopes of f and g for each lambda n1, lambda n1 to lambda nr, lambda n1 prime to lambda nr prime for each intervals. And two sequence cap an and bn are basically that the slopes of f, tuples of slopes of f and g in that interval n comma n plus 1. And here we just define this way, that sup norm of n minus bn, that is nothing but that tends to 0. Basically, that implies if and only for any epsilon greater than 0, the distance of lambda ni minus lambda ni prime should be less than epsilon for all n greater equal to n for some n. So now we go to structure theorem. So basically now we prove a lemma. By using that lemma, we go to our main result of this chapter. So lemma is the equivalent criterion of two equivalence classes. Basically, if G are same equivalence classes, to be belong to the same class or not. So if HF and HG belongs to H1 comma m by H, then they are belong to the same equivalence class if and only if that mod of fx by x minus gx by x less than epsilon for all x greater than m. By using this lemma, we prove this theorem, that the statement of that theorem is that suppose two elements HF and HG belongs to that set H1 comma m by H, and there exists a sequence n such that the limit of that sequence is fn by n and gn by n equal to 1. Then if the difference of their slopes, basically sub norm, basically we take that if that tends to 0, then we can say that they are in same class, same H equivalence class of H basically. And if there exists a k1 greater than 1 such that the next element, the next partition element xni, if greater than k1 into xni minus 1 previous element, and if they are in same equivalence class of H, then we can say that the distance between their slopes tends to 0. So basically this condition is, this subnorm condition is not a necessary condition, it's a sufficient condition. So this is the result of this chapter. So remark is that this condition is sufficient condition, but not the necessary condition. By the example shows that this condition is not necessary. We check this. So these are the chapter 2 basically. Now we go to our next chapter, chapter 3. That means left orderability and local indicability of the group QIR. And it is proved by Ye and Zhao that this group QIR is left orderable but not local indicable. So here we prove that the quotient group QIR by H is left orderable but not local indicable. So it is well-known definition of left orderable group is that a group is said to be left orderable if it admits this total order as well as it is left invariant. And these are some examples that all torsion-free abelian groups, free groups are the examples of left orderable groups. And for non-examples, it's any finite group, finite index subgroup, etc. So now we go to some facts. It is very much well known also, but still I am just discussing that if this is a left order of in a group G, then the positive are basically if that's sign identity, and for the reverse case, if it is negative, we can say negative actually, negative elements. And from this, suppose from this left order, suppose there's a left order on a group G, then always we can define a right order by using that star, that if that relation star G, whenever F inverse, that's that left order that equal to G inverse, you can say. So this order basically turns out to a invariant, a right invariant. So it can be easily say that a group is left orderable if and only if it is right orderable, basically, but not the same order. Obviously, the order may be order is different, may be different. And also is the last fact is that all left orderable groups are torsion free. It can be also checked very easily that there are no finite order element in that, without identity element, no finite order element in a left orderable group. So these are some facts. Now we go to some definitions of that locally indicable group. That is that a group is said to be locally indicable if each of its finitely generated non-trivial subgroups to that Z is there is a non-trivial homomorphism. From all finite and non-trivial subgroups to Z, there is a non-trivial homomorphism. If this happens, then we can say that group is locally indicable. And some well-known examples are torsion-free groups, one-letter groups, the bed group are locally indicable. And some examples are actually interestingly Bn for n greater equal to 5, and obviously all non-left orderable groups. So basically, we proved our main result of this chapter by using this criterion. The criteria is that this proved by Navas that a group is left orderable if and only if for every collection of non-trivial elements of that group, there exists a choice of from 1 to -1 such that the semi-group generated by gi to the power epsilon I, basically, that is not in identity element. This is the main result from where basically Ye and Zhao, they proved also that the group QIR is not left orderable, and also we proved that the group QIR or QIR plus by H is not left orderable. So here are also some facts that if every locally indicable group is left orderable, and in 1991 Bachmann gave a counter example that there is a right orderable group, but it is not left orderable. There is right orderable group, but it is not locally indicable. And we provide here another counter example in the form of QIR plus by H. So we proved this result that QIR plus by H is left orderable by actually taking the idea from Ye and Zhao. They proved by using Navas criterion. We also proved this result by Navas criterion that this group is left orderable, and obviously this group is torsion free. And there are some remarks is that QI plus R quotient H bar, that is isomorphic to obviously QI R plus quotient H direct product QR minus by H prime. And since the direct product of left orderable groups are left orderable, so we can say that these groups QI plus R by H by is left orderable. And interestingly, since the if we take the element fx equal to -x, so that element has order 2, so it is not left orderable, and hence you can, since it is left orderable, so you can see easily that it is not locally indicable also. And also we prove in this chapter that the quasi-isometric group QIR plus by H is not locally indicable. And this chapter, the result of this chapter basically published in a paper, Geometry Indicator journal. So these are the chapter 3 results. Now we go to the chapter 4. That is, the idea is that now we go to, give some combinatorial criterion such that, such that all the elements, which elements basically are in the set Q or group QIRN, and find the center of the group QIRN. That is the main aim of this chapter, to find the elements, which are the elements of QIRN basically. So these are some basic facts. Suppose we are taking that X is a path connected space here, and we are taking that tau is an LFST, that means a locally finite simple cell complex. Tau is a LFST such that mod tau equal to X, and two such locally finite simple cell complex tau and tau 2 are said to be equivalent if this relation holds. The relation is that if there are subdivisions tau 1 prime of tau 1 and tau 2 prime of tau 2, such that there is simple cell isomorphism between that subdivision. that such that also phi realize the entity also. So this relation is an equivalence relation also. So and we denote the collection of equivalence classes as scriptive. And a space X is said to be an LFSC space if there exists a locally finite simple complex K such that not K equal to X. So now we introduce two notions, that is PL homeomorphism of X and PL delta homeomorphism of X. So PL homeomorphism is X is we introduce in this way, that suppose we fix a locally finite simple complex K naught of X for some X. Suppose we fixed. So we say that a homeomorphism G is said to be piecewise linear with respect to that LFSC if there exist two LFSC K1 and K2 which are equivalent to K0 such that there is simplicial isomorphism F from xk1 to xk2. So that is the definition of PL x comma K naught. And for PL delta x comma K naught, just the same thing is happen there. That means all the elements G belongs to PL comma x comma PL x comma K naught is said to be PL delta homeomorphism with respect to that locally finite simple complex K naught, such that for each simplex delta belongs to K1, we get this inequality. We have to get 1 by m less equal to d gx dy, distance between gx and gy by dx dxy less equal to m for all xy belongs to delta. So this relation holds, then we can say that all the elements of PL x comma K naught are element of PL delta x comma K naught. PL delta homeomorphism of x comma K naught basically. So the definition of PLX is nothing but a homomorphism from the free product of PLX comma K to homeo x, and we denote uh, the image of this. Sorry, the image of this homomorphism actually PLX. There is always a free product for similar case. There is always a free product from the group PL delta x comma K to homeo x, and the image of this homomorphism is PL delta x. So now here also define piecewise metric. That is nothing but that infimum of length of the CI. CI means basically C is a path from X to Y such that basically CI1 equal to CI plus 1 0. So this is the definition of piecewise metric, and equivalent metric also will learn that suppose the piecewise metric dp is said to be equivalent metric d if there exist two constant lambda 1 lambda 2 greater than 0 such that this relation holds. Okay, now we prove this lemma that if X be a path connected LFSC space with the condition is that the piecewise metric dp equivalent to the Euclidean metric d, then PL delta X is subgroup of Bilipsich X. We proved this result. And the obvious corollary is that since Bilipsich X, so if an element is if suppose an element belongs to that Bilipsich, then an element also belongs to the quasi-isometry of X. So if X is a path connected LFSC space with the same conditions holds, and if G be an element of PL delta X, then G is a quasi-isometry of X. Now we define a set A in that way. A is the basically the angles between, not only angles, cosine of the angles between two adjacent edges of the simplex delta. So define the set A for the LFSC space K1, and for K2 also define similarly B set. So here basically we go to our main result of this chapter, that the combinatorial criterion of QIRN basically. So let here X be an LFSC space, and suppose G belongs to PL X comma K naught such that G equal to mod F, and her F is a simplicial isomorphism. If there exists a mu greater than 1 such that if we get only the distance between the vertices of the edges with this relation, that means 1 by mu less equal to that distance by the distance of VIBJ less equal to mu. If this relation holds for any pair of where VIBJ are the any pair of vertices, obviously I not equal to J. If this relation holds and the defining set A and B, if that two sets are closed subsets of this R for some ordering of the vertices of the simplices, then G belongs to PL delta X. So here it was there that X is a LFSC space and G belongs to PL X comma K naught, And if we take only impose the conditions on vertices, only vertices, and if we take that two sets are closed subset, then we can say that element PLX comma cannot belongs to the PL delta X. So then also we get this theorem that if X be a path connected space and length metric dp is equivalent to the Euclidean metric d, then in a previously proved that if an element belongs to PL delta X, that element is a quasi-isometry of X. So by previous theorem, we see that if G belongs to PL comma X, PL X comma cannot, and these two conditions 1 and 2 are hold, then G belongs to PL delta X. And by previous result, if an element belongs to PL delta X with the condition that the length metric dp equivalent to the Euclidean metric d, and if the space is path connected, then that element belongs to QIX basically. So if G belongs to PLX, so here we prove that G is a quasi-isometry of X. So next we give a more general result that if G belongs to PL Rn and G equal to mod for F is a simplicial isomorphism and satisfying these two conditions, then G is a quasi-isometry because here Rn is a path connected and as well as Euclidean metric and piezometry are equivalent. So here G is a quasi-isometry of Rn, and moreover G is quasi-isometrically equivalent to the identity map if and only if distance between FBI and VI less than some constant for all elements or all the vertices VI belongs to the LFSC. So by using this result, we again prove the another interesting result that the center of the group QIRA is trivial. So these are the some results of this chapter, and this chapter actually the chapter 4 the results of this chapter 4 is published in Topology Applications in the journal. So now we go to the another chapter that is the structure and properties of the group PLL. This chapter is very much easy because this chapter is motivated by the chapter 3 and 4 mainly. So here PL delta 0 plus R basically the subgroup of PL delta 0 R consisting of orientation preserving PL homeomorphisms which are sending 0 to 0, and then we can easily write PL delta 0 R equal to PL delta 0 plus R immediate product T, and we define these two groups PL delta R plus and PL delta R minus in that way that piecewise linear homeomorphisms with bounded slopes of the positive real line and the negative real line. And then we similarly introduce the invariant SF like SG in the previous chapter, that if we define in that way, then we can also get some interesting result for the case PL delta R also, that if SF equal to the limit set of fxn by xn such that xn tends to infinity and fxn by xn converges, and then we see that if F is a piecewise linear piecewise differentiable homeomorphism of R such that the slope of F are bounded, then F is bi-Lipschitz. And from this result also we can similarly prove that this SF is either a singleton set or a closed and bounded interval. And again, if we define in that set that H prime is looks like that all the elements of PL delta R plus such that the limit is 1, similar to the definition of H, then we can see that actually this H prime is a proper normal subgroup of PL delta R plus. Interestingly, this group PL delta plus R is obviously not simple from the above, and the quotient group PL delta R plus by H prime is torsion free. This is really interesting that this group is torsion free, and also we proved that the center of the quotient quasi-isometric group QI R plus by H, this should be H actually, is trivial, and by using this result, we also proved that the quotient group PL delta R plus by H is trivial, H prime is trivial. So these are the some results, and now we go to some conclusions and future scopes. That in chapter 3 basically we partially characterize the group QI plus. So summary is that actually in the chapter 3 we give an almost complete characterization of the elements of the group QI plus, and in chapter 4 we saw that a quotient of that group is left orderable but not locally indicable, and in the next chapter we provide a commutatorial criteria to determine whether piecewise linear homeomorphisms of Rn, quasi-isometry of Rn or not. And by using that criteria, we establish that the center of the group is trivial, QRN is trivial. The last chapter we saw that some results that the group PLL to R plus is not simple, and the quotient of this group is torsion free, and the center of that group is trivial. And the future scope is that in the chapter 3 we give not full characterization of the group QIR. So it may be a good question that if it is done, if it is, I mean, if we want to give a complete characterization of the group QIR, that is more interesting. And also we check that the H is left order because H is a subgroup of QIR plus and QIR plus is left order. So H is left order, but it is not checked that the group H is locally indicable or not. So it can be a question for that chapter. And also Sankaran proved that there is a onto homomorphism from the group PL delta to QIR, but it is not checked now that is there any surjection from the group PL delta Rn to QIRN or not. So it may be a good question. The last chapter we check, it is not checked that the quotient of that PL delta is left orderable or not. So these are maybe some problems from our results. And these two papers are published in these two journals, and the last one is basically in under review. And these are the references, some references which are actually used in our research. And thank you.